Chapter 5 of the ECE 301 workbook is concerned with Thevenin and Norton equivalent circuits. This is a technique of sort of summarizing um, circuits in a way that can be very useful, especially when you're doing modular designs and you're trying to summarize sort of what a total load or voltage source you have in certain area or component of a circuit. And so, what's called the Thevenin, it's a French name, Thevenin equivalent circuit, could be used to replace a two-terminal circuit that contained resistances and several sources, current or voltage. So the concept is, again, is it's sort of a standard reference that you can use that, again, summarizes the complexity of a circuit with several loads on it. Again, loads meaning resistances. So in the figure below here, or in figure 13, and we're at the top of page 66, the first section of this chapter, this is the classic representation of a Thevenin equivalent. And so just going through the components, just to make sure we're clear. So the Thevenin voltage reference is here. This is usually indexed V sub t, and we have a positive and a negative polarity reference there. And connected to the positive reference is a load or a resistance known as the Thevenin resistance. Again, the subscripts are for Thevenin, little t there, so RT. And then we have an open component or an open circuit here, so that this terminal and this terminal do have a voltage. There's no current flowing between them, but there is a voltage, and this is the voltage of the open circuit, and represented here as V sub OC, all right? So that this sort of way represents how much energy absorption you're getting and generating, and then being able to generate what voltage can you generate across the open terminals there, and perhaps you're going to connect other devices to those terminals, okay? So again, there can be no current flowing through the RT resistance, all right? So there's no current flowing through here, all right? And subsequently, you could conclude then, in the sense that if there's no current here, then basically it's like this voltage source, VT, has to be exactly what the open current voltage source is, okay? So if you were to modify it slightly by, let's suppose you took a conductor, and if you connected these two terminals together, and therefore you had this diagram, then you would have current flowing through it. The idea of connecting that is called a short circuit. And so you would now generate this, this current, which would be called, we would call that I sub SC. So the SC stands for short circuit, right? And therefore, by Ohm's law, you have a voltage and a current, and therefore the relationship between the voltage and the current with the resistance should be given by this representation here. In other words, V equals IR, or I equals V over R. Either way, when you do the short circuit, that current you generated should be the value of the Thevenin voltage divided by the Thevenin resistance, okay? Or that the Thevenin resistance, or the total load there for that Thevenin equivalent, is nothing but this voltage divided by that current that you generate when you connect those terminals, okay? So these are the standards that we use for Thevenin equivalents, and we're going to illustrate how we can generate them by going on to the next page, 67. And so we're going to take about the simplest thing we can do, a circuit with only two loads in it, right? Now, keep in mind, we're looking at circuits that have two open terminals there, right? The goal of this example 1 at the top of page 67 is simply to find the Thevenin equivalent, right? And the technique we want to use, of course, is try to summarize this down as easily as we can. And for example, suppose that the first resistance here is 100 ohms, and the second resistance is 50 ohms, and you have a voltage source here, which is 15 volts, okay? So what we'll do first of all is analyze the circuit with its original open circuit terminals. In other words, we're looking at what can we say about the resistances or the loads, summarizing perhaps from the perspective of these two open terminals. In other words, looking to the left, so to speak. So looking to the left, and we're looking at the representation of, for example, current. If we were looking through that, for example, we could easily say, well, you could easily write a mesh current, couldn't you? And if we did it clockwise, we could represent it this way, right? We'll call that I sub 1, okay? Right? So, so in this case, what we have is a mesh current flowing around there. But if we look around this circuit, in other words, this part of the circuit here, the circuit, you could ask yourself, well, what relationship do we have between these two resistances? For example, if you leave this terminal and come through R1, the voltage source, if you were to come back, you would, if you're completing this loop, you would notice that the two resistances R1 and R2 are in series. So the first thing we'll notice is that R1 and R2 are in series. Okay. They're not end to end. They can't be parallel because, again, you've got a voltage source sandwiched between them there, right? So, but if you start at this, like I said, if you started at either node here, for example, here, and you came through the voltage source and were trying to come back to it, you would come back through both of them, right? You would have no option if we're just looking at the perspective of this part of the circuit, okay? Not looking at the open component, just looking at the closed path that we have, just like we've always done, right? So those two are in series, and so an equivalent, we'll say, would have to be the sum of the two, and that would be what, 150 ohms, okay, right? So what you have is a total resistance of 150 ohms. Therefore, with that mesh current, the I1, you got a total resistance of 150, you got a voltage source of 15 volts. Then by Ohm's law, we know that the current would have to be 15 volts divided by that equivalent. So that's 15 volts divided by 150 ohms, or that's going to be 0.1 or 1/10 of an amp, okay? Right? So what that says, though, then, is that then the original open voltage, in other words, so again, if you just look at the fact that there is voltage between those two open terminals, and we're going to label positive, negative, matching up with the voltage source there. So we know that, well, that voltage between those two circuits then has to be whatever that resistance R2 is multiplied by I1, okay? Why? Well, these two, the representation of in other words, whatever the voltage is that's flowing through R2 is got to be exactly the voltage that's flowing through VOC, right? Because these two, you would think of two parallels, you could think of the voltages must be identical because you have voltage in parallel, so to speak. So even though it's an open circuit there, this voltage has to be the same voltage that is flowing in parallel with it there, okay, through R2. Not through R1, right? Because those two are in series, so we know that the voltage is distributed. The 15 volts is distributed between R1 and R2 in this series connection here, but between the open terminals here, whatever that voltage is got to be exactly the same as that going through R2, okay? Much in the way that if we just had just a general, and if you had another resistance out here, we would know that those two things are in parallel, the voltage is shared. Same thing, the voltage between those two open terminals is shared, it's the same voltage that you have between the terminals of R2. So again, but Ohm's law, we would get Ohm's law, you get 50 ohms, which is the resistance for R2, times 0.1 amps, and you would get 5 volts, okay? Right? So just qualifying again, what this 5 volts is the voltage through R2, the R2 resistance, okay? And it is the same as the voltage between the open terminals. i.e. VOC, right? So again, anytime we have this situation, you have a resistance and you have these open terminals, this voltage VOC, is the plus minus like that, whatever the voltage is here, in this case, if we called it V2 plus minus, these two voltages are always the same, okay? All right. So we have VOC, and we know that the Thevenin voltage is always the same as the voltage between the open terminals, all right? So we are halfway there in terms of designing the Thevenin equivalent for this simple circuit. We needed VT. So you may ask, well, what else do we need? Again, if you go back to the original definition, we need a Thevenin voltage and a Thevenin resistance, right? So you were getting at the Thevenin voltage by determining what voltage must be going through those open terminals, realizing that, oh, all I need to do is find the voltage through R2, okay, right? So now the way to get at that resistance is we have a voltage, can we get a current going through that R1 resistance there, okay? Which we're going to do that by looking at a short circuit, okay? So now what we do is we take the original circuit design, add the short circuit. So in doing so, we'll generate a current. It's called I sub SC for the short circuit current, okay? All right. And if we look at, well, what does that mean in terms of the current going through the other components here, right? Well, what we have here, right, is let's think very carefully so we can understand this diagram, because you can see that I've got listed here that same current going through R1, and you may be going, wait, I don't understand. When you do the short circuit, how much voltage is now flowing from these two terminals? Think very carefully. When you short circuit, we generate a current here, absolutely. But do we have any voltage across these terminals? The answer is no, 0 voltage. So if there's no voltage there, there's no voltage in R2. There's absolutely no voltage, okay? Well, all right, think Ohm's law. If there's no voltage flowing through R2, right, then how much current is going through it? For the resistance now, just for the resistance. What we have here is we have a conductor and we have current flowing, but there's no voltage. So there's no voltage in R2. You've basically rendered that load, you've zeroed it out. There's no current and there's no voltage, okay? So it's as if it doesn't exist. So what you all have now is one current going through, okay? So by short circuiting the open ends of the open terminals there, you're effectively nullify that load, okay? And you have a closed path here with only one current, right? So what we produce then is the fact that, well, then that short circuit current is determined by Ohm's law, that voltage and that resistance. So it's just the voltage source divided by R1, that's 15 volts, all right? Divided by R1 was 100 ohms. Again, we don't need an equivalent in this case, right? Don't need an equivalent because that load has been nullified, okay? So cleaning this up a little bit, you're gonna get what, 15, we'll just write it as 15 100s or 0.15 amps, okay? Right? And so for Thevenin, in this case, R1 is exactly the same as the Thevenin resistance, which is always given by this rate, this formula, okay? That the Thevenin resistance is the voltage over the across the open circuit divided by the current of the short circuit, right? And so in this case, that is 5 volts, which is what we determined earlier, divided by this 0.15 amps, and that gives us 33 1/3, we'll write that way, ohms, okay? So again, let's just clarify what we have here. We have zeroed out effectively the voltage here because we created a short circuit, but there is current flowing. across these conductors. This has been zeroed out, so this load no longer is effective. It's kind of like shut down. There's no voltage, no current, but the current will flow all the way around, okay? So voltage will be released, voltage will be absorbed, right? And then our question was, well, then if I know this current flow and I know the voltage and that is being dissipated, then I know how much voltage is being absorbed. Then I know exactly how much resistance I must have to achieve that current with that voltage, okay? And so that resistance must be the Thevenin resistance in this case, right? And that's 33.3. So for drawing the final Thevenin equivalent for this problem, you would draw it this way. You would draw the voltage source, call it V sub t, which is 5 volts, with the single load RT equal to 33.3 ohms, and then leave the open terminal that way. So that's the configuration. Again, the resistance is attached to the positive polarity of the Thevenin voltage. So again, this is a summarization of this circuit, okay? So this is absorbing and represents all the load that you would get and essentially how much voltage will be delivered, okay? Right? Okay, so that's one example of kind of a brute force technique. You analyze what you can across the open circuit, for the voltage of the open circuit, then add the short circuit, and then try to use the fact that you can determine perhaps the resistance directly. And again, this is a very valuable formula right here. This is the relationship you always want to be using. If you can get two of these parameters, you can find the third, right? In this case, we already had VOC, we found ISE, and then we were able to determine what RT had to be, okay? Right? So, so actually, what I wrote here is not necessary. That's not necessary, okay? I'll just leave that out. Anytime you have these two, you have the third. That's always going to do. The Thevenin, the voltage across over the open circuit divided by the current of the short circuit will always be the Thevenin resistance. Okay, so I didn't need to say that R1 is equivalent to RT because clearly it isn't. Okay, all right. So let's do it again. We'll get some more practice with this. We'll do one more problem. Okay. So again, this is the top of page 68. And at the top of page 68, we have a different situation. Notice the difference in topology. Just for a second, this is example 2. Notice example 1, look at the configuration of these resistances to the left of the open terminals, okay? Now look at them. Notice the difference, okay? From the perspective of those open terminals, looking at the left, very different, okay? All right, so again, we have a closed component over here. We could represent a mesh current here, I1. And I think we see very quickly that if we go back to our world of mesh currents, and again, if our goal is to figure out VOC first, all right, we automatically know that I1 has to be equal to 5 amps. We'll just say by definition. Okay. That's just simple mesh currents, okay? All right. So here's another observation. So the voltage across the 10 ohm resistance is, what could that be? It is, and I'll leave a blank. Let's think about it now. Well, if I know that the current flowing through it, all right, has to be, again, I'm only looking at this part of the circuit right here, okay? All right, Again, there is no current flowing between these open terminals here, okay? There's no current coming out there, right? So that means there's no current coming through here, so that means the current can only be flowing right here, right? So therefore, we know that Ohm's law, that I1 times 10 ohms must be the voltage across it. So that's 10 volts, okay? 5 amps times 10 ohms. Again, there's no current here, okay? So how can there be, if there's no current here, right, then this current will only come through these terminals here and go around and around and around with that voltage source, because there will be no current coming out here, okay? All right, so that's cool. So let's make a note of that, no current. This just helps us understand how to think about these. I'm just writing this to kind of make sure that we clarify. I'm not saying these are obvious observations, but we got to make sure we understand the meaning and interpreting these open and closed circuit components. So there's no current flow through the 40 ohm resistance, okay? So from the perspective of voltage, what is the voltage of the open circuit, all right? Then, you know, we already know that it has to be whatever, in other words, so there's voltage here, there's no current, right? So it's almost like, again, end to end, this voltage has to match the voltage through the 10 ohm resistance. So therefore, that has to be 50 volts, okay? It's the same argument we made in the other problem, right? So this has been rendered useless, and so it's just end to end. The voltage across these two terminals must be the same as the voltage across those. Again, this issue. The voltage here, let's just call this, again, voltage 2 plus minus, because there's no current flow through here. And if there's no current through this resistance has no current, then Ohm's law says there can't be no voltage. So there's no voltage here. So the voltages between those two are the same as the voltage through those two, okay? So that's awesome. So we know that by definition, the Thevenin voltage is always the same as the voltage across the open circuit. So we've got half of it. Now we just got to find the resistance. So what we'll do is add the short circuit. Okay. And with our goal of seeing if we can figure out how to determine the, let's say add a short to determine I sub SC, and then obtain, so it's good to have the strategy, and then obtain R sub T as the ratio, okay? That's our technique we're using right now to get these equivalents. Again, right? So let's do that. So it's a good idea to just redraw it. So we have 5 amp current source coming over here, drop down 10 ohms here, and draw the 40 ohm resistance here, and then we're connecting. So we'll just kind of represent, we've wired them together, okay? There's your short circuit. And in doing so, we'll represent that current as ISC, okay? Right? So in this case, we know there's no voltage here, but we have current. So we have a current flow here. We have this 5 amp current source coming in. And in this case, what's happening is we see current splitting, right? So this is an interesting situation, different than we had before, right? So just for a sample, I want to flip back just to show the difference here, okay? Notice the differences in the relationship between these resistances when we added the short circuit, okay? There was no voltage here, and it effectively shut off this load completely, all right? And then we said there's only one current flowing in this case, all right? This is different. See the difference? When we short-circuited here, all right, we don't have a resistance in parallel with it. Why is that 10 ohm resistance not in parallel with it? Because of that one. You see what I mean? Interesting. It does not zero that out. Neither one of these are zeroed out. So what's happening this time is that the current is actually coming, let's say the 5 amp, we're going in this direction. The current is coming through this part of the node and it splits. It splits either to the 10 ohm or it splits to the 40 ohm, right? So it's a closed path, and you could, you know, we've talked about these kind of circuits before, right? So again, very important to know what you see is sort of representation of you know, alignments of when things are in parallel or not. In this case, they're not. And so in terms of, you know, the voltage here, right? We cannot say the 10 ohm resistance has zero voltage now because we have a resistance in front of it, right? So, but we can use CDP, right, to determine how the current splits across those two resistances. So in this case, the short circuit one that we want, okay, again, thinking about it's going to be the current that takes this path. I'll indicate in blue. So it's the same current that comes through the 40 ohm resistance, right? Right, not the 10 ohm resistance. This current between those two nodes that we've now connected together is the same current, right? It flows through here, then comes through here. It's like these two, this conductor is basically in series with it. It has to come this way, all right? No option. So in that case, if you go back to CDP, I use the resistance of the neighbor. So I'll take 10 ohms divided by the sum of them, 10 ohms plus 40 ohms. That will be weighted times the 5 amps, the original current source, and we will determine that's got to be 1 amp, okay? Right. So what that's saying is that with this 40 ohm resistance, you're going to take 5 amps. That looks weird. That's 1 amp. 1 amp will go this direction, right? And then you'll get 4 amps through that direction, okay? Because KCL, we know the incoming has to equal that sum of the outgoings. So you're going to get 1 amp going this way, and you're going to get 4 amps going that way. That makes sense because look at the sizes of the resistances. This is 4 times larger than that, which means that ampere will be 4 times smaller than the other one. Okay, so that's consistent. All right. So therefore, using our formula, RT as we have over there, VOC over ISC, then we know the Thevenin voltage is 50 volts divided by 1 amps, which is just 1 amp, which is just 50 ohms. So for drawing the Thevenin equivalent, I'll just say TE, draw the Thevenin voltage, VT, which is 50 volts, plus minus, connected to the Thevenin load, which in this case, RT is equal to 50 ohms. So this circuit, just looking at totality here, there's its Thevenin equivalent. It's equivalent to a 50 volt voltage source supplying a 50 ohm resistance, this configuration, from the perspective of those two open terminals, okay? So again, determine VOC first, then use a short circuit, see what the resulting current flow looks like when you close that, when you close it up and have the short circuit. You may nullify some resistances like we did in the last example, or in this case, you may see a current flow which has exit ramps thinking, oh, I can probably figure out which portion I'm interested in. In this case, you only care about the current through the short circuit. That's what the Thevenin, the resistance needs to get the resistance value, all right? And that goes back to the original definition that I showed before, okay? We'll do some more examples of this approach using resistances and properties thereof to determine Thevenin equivalence in the next section.